so there are two more, including today, two more lectures. And then we'll cover, I'll try to cover some basics of ecology and try to connect to so-called symmetry, the notion of symmetry protected spaces, pieces. Topological, sorry, symmetry protected topological basis. That's the one. And then even last time I talked about that. So that's first. So the is exam, and then this counts 50% of your grade. Yeah. So the rule is no laptop, but iPad or like a picture, the one tablet is allowed, but no internet. And also only PDF reading, only PDF reading. Uses for only for PDF reading, so that's okay. So the whatever textbooks or whatever papers, if you want to just download it beforehand and just put it into like a PDF app, then you can take a look at it. It's Kaizen, so I mean it's the same thing. I mean it's bringing the logic textbook or print out paper. Instead of doing that, you can use the data. I haven't created the file yet. The plan is yeah. If you come to the lectures and then listen to the lecture, it should be okay. It should be okay. I think most of them are like basic one, or like the one I show you in the lectures, and so it should be okay. I haven't created examples, but all the content is from the lectures. Okay, that's that case. Any question about the example? Okay, if not, let's get started. So we're going to talk about XLP model. The model is something like a problem of so that's the AKLP Haldane. So essentially what you need to do is the project in two states. To each method is essentially projecting in two systems. So I mean if you write down like this way and then just connect, so each the balance you have the spin 1 half, but here you have a spin 0 state. So you have a spin 0 state like this way, but at this formed part you have to symmetry. So that symmetry over the P hat. P hat relationship. So just here you just act on the simplified operator. P hat. So P hat is just a silicon. And the P hat like this. And this can be used as a root 2 times root 2. You should like this. Okay. Now, so you started no, yes, last week I tried to explain the so-called matrix. Alright. So MPF, the state is so this is the ES, and you use the sum of trace of A sigma 1, sigma F. So, okay, okay. And then rule is of the so last time I also explained very well. It's as follows. So for here, everything is P1. P1. So therefore sigma is something like. So this corresponds to this is plus. This is minus. And this is current. So like this way. So therefore sigma I is plus minus or 0. Okay. And then rule is as follows. If this A operator is two-dimensional matrix acting on this part. So I call that this part is something like one state is something like this. The two state is something like this. Okay. So you have a plan. So then you just look at that, what's going to happen in this bond. Okay. In this bond. Okay. So if you have this plus, then you assign a plus. And then this one is always has this one is always here is like one state. You can two states. Okay. So therefore, so only two components non-trivial. One component is non-trivial minus square root 2 here. So this 1 over square root 2 is minus 1 square root 2 because here times 1. So minus 1 square root 2 is over square root 2 coming from here. So 1, this is corresponding to 1 state. And this corresponds to 2 states. And even 2 states that have a minus 1/2. And this one coming from this coming from this is coefficient in front of of 2 states. And this is coefficient of plus state is here. So when you project sinusoids, you just have a 1. So therefore you have 0, 0 minus 1 over 2. Okay. So now we consider that down case, this is minus. I think it will be better to use one thing which we have to improve is the quality of choke. And section. So down, and you have all the possibilities like this way. So this is two stage to one stage. So this is two one entry. So only two one entry is on here because one becomes two. So now two become one. So therefore, for A minus, it's only non-trivial components here, and which is square root 2. 1 over square root 2. So this is 1 over square root 2 times 1. So this is coefficient of this one state, and this is coefficient of minus. Okay, another possibility is something like this way. So let's consider this way. Then this way is become like this way and this way. Oh, okay, maybe it's the opposite this time. This one becomes one. And if you how to say symmetry as this becomes 0. 0. So therefore a 0. A one component non trivial, and which is 1/2 because not 1/2. Yeah, 1/2. Sorry. So this is square root 2 plus square root 2. So this is coefficient of 1, and this is coefficient of 0. So here you have 1 over square root 2 here. So this guy you need to multiply. So plus and minus you have a coefficient 1. But for 0, so you have coefficient 1/2. 1 over square root 2. You have to multiply this which is 0. And for 0, we have another matrix element because of like this way. And this is 0. So here, so therefore 2 becomes 2. So the 2 component is non-trivial. It should be minus 1/2. So this is minus square root 2 times 1 over square root 2. This comes from the coefficient Q state, and this is the coefficient of the unit. That's I failed to explain last time. Okay. So now what we need to do is the so what we need to do is just include this all the metrics, G metrics. So one is this guy, the other is this guy. This guy, and plug that into here, and I'll do this. And then schematically, people just write down this state. So this is the collagen like the sigma. Is the sigma. Schematically, you can just write down that A. Sigma 1, sigma 2, sigma 3, like this. Schematically, people can write down like this. Okay. Okay, and then so you can easily see that these. So you can see anti hidden anti-ferromagnetic magnetic order. So last time, what I mentioned that if you have like a plus minus 0, plus 0, 0, minus 0, plus minus 0, plus and so on. So if you look at the each in one state, if you get remove 0, you always have the plus minus something here, like a plus minus plus minus plus minus plus. So that's because of here when if you have the plus and minus, you have like this way, and next is 0. Because if it is 0, you have to take the what I'm doing. Oh, like this way is 0, you take like this way, and the next is always like plus, like this way, and so on. So if you do like this way, so this is plus minus 0 plus, and so on. So this is 0 and so on. So you always have this hidden antiferromagnetic bond. But if you look at this one, it's very simple. I mean, it's A plus is this off diagonal one, like understand? Lower down off diagonal entry. But the A plus, so A minus is upper off diagonal entry. So the help of, I mean, so if you have the A plus square is always 0, so you can see A plus square is over 0. The same thing, A minus square is over 0. Okay? So the help. So here, if you put that A plus, like a plus in order, you get over 0, right? If you do the trace of this one. So therefore, such a state cannot contribute. Only the state that have the hidden antiferromagnetic order can contribute this state. So which is you can easily see from a matrix evaluation. Okay. Now okay. So now also we try to compute this one. Which is something like this one. Like this one. So we want to compute like this thing, which is sum over C sigma. First. Like this. Okay. To do that, so what we need to compute is this. What we need to compute is this one. So alpha prime, beta prime, which is sum over a sigma from sigma L. Alpha prime, beta. Like this. So we want to compute this. So we call this one as alpha, beta, alpha prime, beta prime. Okay. Like this way. So we just need to compute. What we need to do is compute and fill up for instance Two small ones is equal to sum over a sigma. T1 sum over a sigma. T1 sigma. But dual components are only for L plus. L plus. Okay? So the output is equal to 1 half. Like this. I mean, just do the exercise. Okay? So, okay. Yes. So like this way. And if you compare it, what we have is as follows. So what we have is as follows. So sigma and then a tilde component and alpha beta, alpha plus beta prime. So this plus is coming from this one up, and this is 2, 2, 1, 1. So that's all of that. Minus is contribute 1 half, and this is 1, 1, 2, 2. Okay? And the other is coming from 0, the 4 components. Okay, so then you have 4. So 1, 1, 1, 1, 4, 4, 2, 2, 3, 3. Minus 1 fourth or 1, 1, 2, 2. Minus 1 fourth or 2, 2, 1, 1. And if you write down this matrix, tilde, you can just have the following matrix. Like this one. Fine. 1, 2. 1, 2, 1, 2. 2, 1, 2. 2, 1, 2. Like this. Like this. And then what I did is this is 1, 1, 2, 2, 1, 2, and 1. The same thing. 1, 1, 2, 2. Oh, sorry, something strange. Like this. Okay, so now for this one, so this one is equal to frames of this tilde to now. Okay. So to do that, we just need to diagonalize this measure and find that eigenvalue. Okay. And then we need to diagonalize this one, and then this is 3 over 4 minus 1 over 4 plus 1 over 4 minus 1 over 4. Now for this is 3 over 4 to the out plus 3 from 4 to the out. Okay, so let's see what's wrong with it. Okay. So now, this is normalization. So what we want to compute is that they are as follows. So first, we want to compute so-called regression function, and then to see we want to like this. So we want to compute this, and then to the system in gaps, we want to show this is exponential decay. So we want to show that this one is e to the minus whatever r over 2 proportion. So if it is the exponential this decay, this means the system in gap. And this is called short range interaction. So another thing we want to do is so-called something we call, and if you take r equals infinity, then this goes to 0 when r goes to infinity. The other thing we want to do is, the last time I told you briefly, saying that this string order parameter. So instead of putting just string variable here, you just have a point. So that's what we want. And so this is string over parameter, and then as we will see, so this will just become non-zero. Become non-zero when the when this j element j goes to infinity. That's what we want. So this is non-zero, so this is string over parameter means that so this is very highly non-local part. It appears in the middle. And this one is, of course, 0 for trivial cases. Trivial cases, Hamiltonian is, of course, adaptation, sum over Sj. So therefore, all spin is 0. Therefore, you put the 0 here, of course, you become 0. So e to the 0 is 1, and it becomes 0. But for equality, this is not 0. So therefore, you can, distinguish two cases. So trivial phase and the Haldane phase. So we want to show this one by using this MPS. Using that MPS. It's not difficult because we already have the preparation. So to compute this one, like this. So we put spin operator here. So here is spin operator. You put the spin operator here, in here, then to put the r plus 1 phrase, you put the spin operator here. They compute. So this is the r phrase. So that's what we want to do. So now what we need to do is to compute this state, I call it equivalent. Like this. Okay. So that's what we want to compute. Therefore, this one is equal to sum over sigma and sigma prime. So this is sigma and sigma prime, and then sigma alpha prime, and then sin alpha, sin sigma s d, and then here we have sigma prime, beta prime, like this. That's what we need to compute. Okay. And the sigma minus sigma prime is of course the plus minus 1. That's what. And this one is equal to under of sigma prime as if the and B is simply because diagonal, right? This is plus 1 and minus. Sorry, SB here is more likely 1, 0, 1. Like this. So therefore, it's diagonal. So what we need to do is sigma alpha prime and sigma beta. Sigma is equal to plus minus 1. And this can be written in the same basis as before. Here. So what we need to do is that so since there is sigma here, all 0 components do not contribute. You need to multiply sigma. So therefore 0 do not contribute. Only contribution is plus and minus. Coming from plus minus. So what you get is as follows. 0, 1 half, 1 half, 0, 0, 0. Okay, that's what we have. So the output so this correction function is equal to trace of minus 1 half from 4 from half from 4 and then to the r and 1 like this one. Okay, and you just need to diagonalize it. If you diagonalize it, what's going to happen is as follows. So O is something like first 3, 1, 1, 1, then O on 4, and 1 half, sorry, 1 half, 1 4 is equal to 3 over 4 minus 1. So you just diagonalize. On the other hand, or maybe O is not good. So better, maybe let's say M, and inverse, M, inverse, and also M, 0, 1 half, 0, M, 0, 1 half, 0, like this. Therefore, this becomes minus 1 half, minus 1 half, 0 for 4 to the r minus 1, minus 1 to 4, r minus 1. Like this. Okay, so then if you compute this one, what you get is that the minus 1 for 4 to the r, 0 for 4 to the r minus 1 plus minus 1 for 4 to the f minus r, 3 over 4, r minus, like this. Very simple, very simple computation. And then precisely speaking, I have to normalize it. This one I have to normalize by BPA, BPF, and take algorithm infinity. So if you take the algorithm infinity, what's relevant is that the element of infinity, this term is dominant. That's because the L, power L appears minus 1/4. But here you have 3. This is bigger than this one. Absolute value is bigger. Therefore, this term will dominate when L goes infinity. The same thing happens in is erased. Oh my goodness, things are erased. Oh gosh, I do. So, I just calculate this one on time. So this term will dominate while L goes infinity. Therefore, you need to take a ratio. So when L goes to infinity, what's going to happen is that the minus 1/4 to the R, 3/4, L minus R minus 1 divided by 3/4 over that, which is equal to 4 times minus 1/3. That's all. Okay. And if you take the R goes to infinity, this becomes 0. So therefore, it's a really exponential decay. So to the R. So therefore, system is gapped. That's how we show the correlation function. Okay, any questions at this moment? Now, so let's look at the second goal. So this second goal is PBS. Inner product is non-zero. That's what we want to show. And then okay. So we define project operator P deal. I call it P deal, which is the following. So you have like a plus, minus, and zero. You have the 3 states, and this projection for all the project is 0 state. If you have SD is plus minus 1, if you square is 1, so 1 minus 1 is 0, right? On the other hand, if you have a 0 in SD component, you have a 1. Therefore, this is the projection operator. And we just first try to compute the following. So J, J1, we have 0, Jn. Thank you. Okay, so that's what we are going to compute first. Okay. So this means that the so this was project then states like a J1 states to the 0 and J2 states to 0 and so on. Okay? And here what we need to compute is state tilde. So alpha beta T tilde is something like sum over sigma t equal to plus minus 1 and 0 1 minus sigma squared a sigma alpha prime beta beta plus. So now, this one only just apply when sigma is equal to 0. When sigma is plus minus on this term 0. Therefore, we only look at the 0th part of a component, which is diagonal. So this is okay. And so now for this one, it's more like a rate of the tilde to the n and tilde to the L minus n. And if you compute this one, that is the same computation as before, and this one is equal to I don't know how to say. 1 over 4 to the n, 3 over 4 to the L minus n, minus 1 over 4 to the L minus n, plus 3 times minus 4 to the n, plus L. Like this. That's it. Then you can just take a ratio. You can take this one, and take L goes to infinity. So then this one, when L goes to infinity, you will region. One over 3. Yeah. 1 over 3. Okay. So that's what's going on. Is it okay? So this term dominate and this term dominate where L goes to infinity. And if you take ratio, so 1 over 3 appear from here. And then you get on. So this means that at the site J or whatever J, the probability that appear 0 is 1/3, which is very compatible. Because we have only 3 states, and to have a 0 in that site is really 1/3. Therefore, you have 1/3 again. Okay, so that's what we have. So now let's try to compute this one. So I will erase the envelope. Okay. So here, so if you have the inner side have a 0, you get a vanishing expectation value. Okay? If you put the SD of L side is 0, numerator is 0. The same thing. This one is 1. If it is 0, numerator is 0. So therefore, it should have plus minus 1 to have a non plus minus 1. Okay? Plus minus 1 to have a non-zero expectation value. But we only need of the to have a plus minus 1, you only the probability is 2/3. 2/3. Okay? And then in the middle, you have either 0 or plus or minus. Okay? In the middle here. So now what we are looking at the J. Let's see, J side. say SJD, and then here like this way, and in the middle you can have the whatever state, and that contribute to this exponent. But we know that if we have an hidden anti-ferromagnetic order, therefore the number of plus and the number of minus should be equal. And also in the middle, even if we have a 0, there's no contribution to here. Therefore, in total, if you take L goes to infinity, and then this L and J, so that the L minus J goes to infinity, so that this exponent becomes 0. Because the number of plus minus is equal to the same, and then 0 does not contribute. If you sum plus minus, plus 1 minus 1 is 0. Therefore, this becomes 1. Therefore, this becomes 2/3. Because we have 2/3 and 2/3 contribution probability. So therefore, this one is equal to. So therefore, which is on D. So this string order parameter provides non-zero answer. Non-zero answer when L goes to infinity, and then L was J. So this is the length between them becomes okay. So that's what we saw. So dimension. So here this. So this is operator, string operator. But the whole string and trivial vacuum. Okay. So therefore, this becomes all the parameters that distinguish Haldane phase and trivial. So dimension, so if you have the S is SH trivial and plus 1 minus SH, say, AKRT, so you have an S here, and 0 to 1, and you have some critical parameter S star, and this is called trivial phase. And this is a Haldane phase. Okay. Also, unique gap ground state. But here, order parameter string is not equal. Whereas here is used. Here is used. So that's how that's why we call it the string order parameter. Any question at this point? Okay. Maybe was it too quick? I hope it was okay. Okay, and the summary of current stage is that the So H is reality. So unique, gapped, ground state. Okay, that's it. And again, so the correlation function. So gapped means the correlation function. It's exponentially okay. Yeah, actually, this way is something like 1/3. As per the number. What is it for? I don't remember. I think. But exponentially okay. So this is short for integral. Okay. And then spring order. So now we want to consider open. Open AKLT. So if you consider open AKLT, isn't it something strange?
So the coefficient of the diagonal, it should be 4/3 and multiply the minus 1/3. Or maybe 4.
Good, thank you very much. So now, so we want to have the so we just want to have an open case. If you have an open case, you have a schematic in the bond part, but you have the edge model right here. Or edge model. Yeah. So the outpost, so open. So therefore, what we have is that the we have energy spectrum here, and then you have a ground. So the ground state is for like a degenerate whole state, and then you have so full degenerate ground state and gap. So open, if you have an open end, you have this kind of picture right here. So, and for each edge, you have a D, like a D to D equals 3 on the shelf. So this is the AKLT. And then the Heisenberg also has a similar to this. In fact, I need to mention the short range interaction. Heisenberg spin chain shares the same speed. So H Heisenberg is just a sum of Sj plus 1, J, like this. On the corner. That's the same. But this kind of, I mean, so the showing this it has a unique gap stated has not been done exactly. Everything, but numerically and so on, it's already good. So this is HLT Haldane case. Heisenberg case. So what we have is as follows. In numerically, it was observed like this way. This way. And this is the fourth state will just form the spin 1 and spin 2, spin 0 states, and then there's a small gap in the middle. Very small gap, very small gap up here. And then after that, you have the big gap up here. It's very thin. Maybe. Okay. So this is numerical. Check. And to see this V2 cross V2, so somehow if you just make closed spin chains to the open spin chain, this V2 cross V2 symmetry will show up in the AKLT. And then this can be seen by using so-called Kennedy-Nagasaki transformation. Kennedy-Nagasaki transformation is this D2 plus D2 will appear very manifestly. So I'm going to talk about the so-called Kennedy-Nagasaki transformation. So this is 1992. Okay. So yeah, before going that, I will consider the following model. So the candidate, so we can consider that. So H lambda is something like this one. Like this one, Hamiltonian like this one. Okay. So when you set the lambda equal to 1 and equal to 0, H is equal to H is alpha. It becomes HLT. When you set the H, let's say, D goes to infinity, this is H becomes trivial. So this D goes to infinity, this becomes dominant. On the other hand, you set H lambda goes to infinity, this becomes H ID. Anti-ferromagnetic ion. Because if you only look at this term, it's really ion model which appear in the whole this. Okay, so that's the case. And then, so what's really happening is that the lambda. So what's really happening is that the lambda is equal to 1, or something like that. So what's really happening is the phase looks like this. So this is the item phase. This is the trivial phase. And this is the, here is the Haldane phase. So this one is the Haldane phase. Haldane phase. So that's what's really happening. And then here, so as I mentioned, if you go to the open case, you have a d2 cross d2 treatment will appear, the OH model will appear. And once you take one of the ground state, this d2 cross d2 symmetry will be spontaneous broke. So that is called spontaneous symmetry break. Because, I mean, if you only look at this Hamiltonian, you have H mod Z2 cross D2 in the Hamiltonian. However, if you pick one of them, if you apply T2 cross D2, you get different ground state. Therefore, that like once you take the choose the ground state, that automatically break D2 cross D2 symmetry. Therefore, that is called spontaneous symmetry break. And this only appears in Haldane phase. This only appears in Haldane phase. And then, so trivial phase sizing model case, we don't have such a difficulty. And then this hidden D2 cross D2 symmetry. So hidden. D2 cross D2 symmetry breaking. Spontaneous symmetry breaking. So people often write the SSB in physics community. Can be seen by using so-called Kennedy transformation, which is a very non-local operation you can introduce. So U Kennedy exactly is product exponential. So it's very, very non-trivial operation you can do. So here, you just count over. So if you have a state, you have a state like this way. So here you just sum over everything by sum of Sj to the k minus 1. This is k state, and 1 to k minus 1. Sj, and then here you have, so here you have x. You have an aspect of k. And put, so this sum that up or multiply, and then put it in next point. Okay? And then you just multiply k is equal to 2 to the l. This, and then you okay, that's okay. And if we try to understand what's going to happen with h lambda d and ukt and ukt. So what's going to happen? I call it this one h2 lambda. And if you go to here, so this is very non-local. transformation. Okay. The very non-local transformation is very similar to what we saw in this Jordan Wigan. Transformation. Do you recall? Last week, as far as I remember, I just rewrite Sx as d as y, as y as d in terms of Fermi, right non-locally. It's very similar to what we did for Jordan-Wheeler transformation. Here, similar. Do you want to recall? So, yeah, last time. Like this. So this part is very non-local. So what we did is that you just consider a site like this way, and then you go to, so this is J side, J side, J side. So for J side, you just consider like some string is attached to J side, which is e to the 5 sum over NL, and you just apply F J like this. So you just start with 1, 2, 3, blah 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 to the J that will appear here. So it's very similar to Jordan. And we will see how this Hamiltonian will change under this transformation. You will see that we keep the two cross state. But before that, let's take a break. And if you have a question, please.
这是上头来，我们是 HK 关系的作用是后面一个的血得到前面一个的血的这种，就是这边是第二，然后它这个到这边，它下一步是第二得两，然后 A 上的规划是这个解，这个也上的它是自学习，所以要负一。就是很有道理，但是其实是个在可以。我身上有其实所以说，你说以前的一个如果这边是一个要是圈里面是一个苦，那就是说你后面一个是 A 不是一起，对，我想它就比较。把你翻过来，然后写它如果上的话，这边就没有；我是翻的话，就下上，然后这边就会。哦，对，这边是我这样。这样。不同的系数反正是不同规。那么前面这里是这里是规划，规划的情况。 我其实你就是我是哪个位置最小？在中嘛。这我是要记的是，我真的不好意思，他这个记词。这是期望值，这个其实是很简单的。啊，这个画，他们就是这个画。他这里头跟脑子就是或者是如果有两个相比的 A 正 A 正，或者说这个对，但是我不知道这个机有没有清楚它是别的。对吧？因为客户帮他围绕这个就快有点平，是太听话了。就是算幸福的。一起有没有因此？我记得以前这样，看我有的，他会做一个这个号，就是他的一级是这样，也是这样子，啊，是这样的。是，我也是这样的，我就去点。你刚那个背后图表，你那个太神了吧？
And then summer. Yeah, I didn't bring up the note. Sorry, I don't have time. Sorry about it. Oh, I told you this. I do.
那这个系数是什么？对，进入铺垫，会换。对，还是食材量上，对表那个讲究。那这个是我，我们现在还有一个叫什么3国演，不知道是什么，神秘的图案，有内劲。
Question? Yeah.
Well, in the product can be written this way or this way. Okay.
Oh, okay. Oh, sorry. Okay, this one is already. Sorry. I think sorry. I think the very basic thing. So, if this is not done, so we have so this is BBS. Is some of a sigma trace of the sigma 1. Sigma L and the sigma equals sigma L. Okay. And then yeah, can the definition. It's the same as what we did. This one. And so you just create a free PDF and then put the projection operator. The same. But okay. And then so here you have a indices alpha beta. So here you have alpha 1, beta 1, and here is alpha. Okay. I don't know how to do alpha 2, alpha 3, alpha 3, alpha 4, and so on. So this is the same as what we did with alpha 1 and alpha 3. And it is for another matrix. So, and then this is the 1, 2, and alpha 3, and so on. And at the end of the day, if you need to take a trace means you need to take like this. So indices at the end you have alpha L, alpha 1, right? Alpha. So yeah, so you need to have so this is alpha L and alpha 1. Like this. That's the meaning of trace. And then you have an indices here, you have a sigma 3 and so on. And if you take the inner product, which means that you need to take the inner product of sigma 1 total sigma L, sigma 1 total sigma L. Yeah. Like this here. So this means so you need to sum over all indices here. So which means that the so this is one DPS, and the other is like this one. Yeah. And you need to sum over sigma 1 and sigma 2, sigma 3, and so on. To check in the graph. And you need to sum over. That's what I mean. So essentially, what we need to do is different than called C sigma. And this is sum over sigma and C sigma. Yes. That's it. But the schematically, like, you can start around like this. Pictorial. And then if you insert S and so on, you can put something operated here at that side. Because you have S, C and so on acts on this sigma. So essentially here you just insert S, C, some such J that acts on the J state. Yeah. That is the so here if you put like this way, so the matrix S C sigma 1 side sigma 1. So here you have sigma 1 and sigma 1 which are the matrix. And that's the on the top. Is it okay? Sorry, my expression is too fast. I'm sorry.
公开算法。就教他那个叫什么 正交的，然后你正交就把它乘一起就行。这是什么？一个形容一个差交。这个指向大家。基本就是现在这一项就是，那你看到只有相同正交的它的那个系数才乘以项，相就是它那个就是前面系数，它们累积就是前面系数的除法嘛。我这是希望。这是确实。对，然后右边那个开始是要一点。对。那边其他用就是有点像那种带球的约定，那种3个球的就是3类次，对吧？就是 A 阿尔法 E 阿尔法 A 阿尔法然后乘一圈，然后乘回来那你猜球和约定的行。然后这个它就是对的就是那个，你就觉得那个地方。
Okay. Shall we review? Okay, so let's consider the penalty Takasaki transformation. So during the break, so students asked me this tutorial explanation of this EPS phase about that. Yeah, I mean, if you have questions, just you can bring during the lectures. Even after lectures, okay. If some students do not understand my explanation, which means that many students do not understand my explanation. So some students get stuck, which means that I need to repeat the explanation. I need to improve. Okay. Oh, and then yeah, so this is the first time to have a course on statistical mechanics, and then for me, even for me. And if you need to do a pinch.
Okay.
Yeah, just tell me your honest opinion. How to improve the lecture or whatever, or your personal feeling on this lecture. I heard that this statistical mechanics really depends on the lecture, like a teacher, who the content really depends on teacher.
Yeah.
So this time I pick superconductivity and then this quantum spin chain spin model. I'm not sure. So if you think some other topic you prefer to, you like to listen, or like a next if there's another occasion, just give me some honesty or opinion. Okay. Fine. So let's do that. First of all, so this. So this transformation, so E to the phi I, so Sj, E, and Sk, X. So this one, if you square it, this is always 1. Okay? So this is 2 pi I times whatever. B is plus minus 1 or 0. So therefore, UKT is equal to 1. So for example, UKT inverse and UKT noise is equal to UKT. So that's the case. And then and also exponential of so if time of n minus 1 given, so this is always the unit matrix. Because so this is even, so this is something like a 2 pi I times some integer times sx, right? And then sx is always like a plus minus 1 or 0. And if you have a 2 pi I, it's always 1. Okay, so if this is off, then this is the unity constant exponential pi I times skx. And this is equal to 1 minus 2 times sx. Okay. Sure. Do you know why? Let's suppose exponential pi I is xk. Okay. Suppose this one as the eigenvalue plus 1. So this gives you minus 1, right? And if you took the plus 1, here plus 1 squared is minus 1. 1 minus 2 is minus 1. And the same thing, minus 1 will give you minus 1. 1 minus 2 times minus 1 squared is equal to minus 1. So just plug this one into here, you get that minus 1. Okay. And if you have a 0, you have 1, right? Okay. So therefore, here, if you put a 0, you get a 1. So this is 0, right? So therefore, so this operator becomes 1 minus 2 times skx squared. And we recall after this skx. Sorry, I got confused. Let me check. Am I correct? Yes. And then, so x is equal to 0, 1, 0, 1, 0, 1, 1, 0, 0. I'll probably check this way. Is this okay? Okay. This is correct or not? Let me check. Am I correct? Sorry. Sorry. Yeah, I think, oh, sorry. What's missing? Sorry. I actually did the 1 square root 2. Okay? Then, so if you square what you and times 2 is this is equal to 1, 1, 1 minus 1, 2, 1 become like this. So if you square it and multiply by square it, multiply by 2, so you get this one. Okay? So this one is equal to 0 of that really like this. It becomes like this. Okay, so that's what's really happening. Okay, and let's examine what it means. Okay, so therefore, so this means that if you have a case size of case size plus minus case size is mapped to minus plus case size. Okay? So since the matrix is the minus 1, minus 1, minus 1, and the plus 1 is like this way. It's mapped to equal to minus 0, 0, 1. This is plus, it's mapped to minus like this. And similarly, if you just have a minus, you just have a minus plus. Okay. So the output you get this. And you have a 0, a minus of 0. So that's what's going to happen. Okay. Okay. So therefore, what's really happening is that so if it is so previous one is odd, so you have this operation. However, if it is even, you have the state is as before. Okay. So therefore, what's really happening is that so this operation. So let's examine what's happening. Suppose you have a hidden anti-charge ferromagnetic order. So you have a hidden anti-charge order. And then let's apply 1 by 1. So if you apply this Kenneth U, and then you Nagasaki, you just apply these states. So let's call it Sigma, and then U Kennedy Takasaki. So if there's nothing, so it's just even, so they just have a plus sign. But this is the even, so you have let's see. Yeah, so now we have, if you move that here you have a plus one, which is off. So therefore, after the sign difference, so the plus is mapped to minus. And the minus is mapped to plus, so therefore this becomes plus. Okay? And if you sum them up here, you get 0. Okay? Because hidden anti-ferromagnet, if you sum them up, you get 0 or even. So 0. So therefore, here it should be plus. Okay? And then 0 is still 0. And in either case, you have a odd one, but 0 is not to 0. I don't care about the sign, overall sign. And now here, it's minus still, like if you sum them up, it's still odd, right? Plus one, plus one. Now for minus is mapped to plus. Okay? The next 0 is mapped to 0. Okay? And if you sum them up, you get 0. Plus minus 0, right? Therefore, plus is plus. Okay? Next, if you sum them up, you get a 1, which is off. So therefore, minus is mapped to plus. Okay? Okay, so this is hidden anti-ferromagnetic. Okay? This is hidden ferromagnetic. It becomes plus 0, 0, 0, plus, plus. So what this can be Nagasaki translation is so hidden anti-AF open to hidden ferromagnetic order. Do you understand? So this very normal translation will do this kind of job. Suppose you put the some defect, change the like this, change like this. So if you change the, so this is some defect inside a hidden anti-ferromagnetic order. Then apply the same thing, same rules in here. Plus minus plus minus plus means if you sum them up, you get a plus 1. Odd. So therefore plus is mapped to minus. Okay? And then so if you sum them up, what's going to happen is even. Okay? Plus 2. So therefore minus should be minus. Okay? So therefore if you map them to the ferromagnetic, here also have some defects in here. So all the other is plus plus, but the defect part becomes minus. Like this. That's what's really happening. That's the meaning of this Kennedy-Nagasaki transformation. So now, before I go ahead, so we want to compute this UKT, Hamiltonian UKT, but so this Hamiltonian is lambda T Hamiltonian. As I mentioned last time, so before the break, I told this is AKLT when you said lambda equals to 1 and T equals to 0. That's not true. Because AKLT, you have terms like 1 over 3 S squared. This term up here. But this is just usual Heisenberg transform. And so to see this transformation, we will see the following thing. Suppose let's compute UKT as J and the vector. So by the way, so do you know this one? B to the pi is x as x b to the pi as x is equal to is vector, but e to the pi I is y as x, e to the pi I is y, e minus x. And then here e to the pi I is c as x. So this is okay. So this one we need to is the configure to zero calculation. Okay. or minus. Either is okay. Plus minus. Since it's pi I, plus minus doesn't matter. Now let's compute this one. Let's compute this one. The computation is the as follows. So each side, so different sides, the S, the spin, where spin operator commute. Different sides like a SJ, whatever alpha, and the SK, beta, they commute when J is not equal to Q. Okay. So therefore, if you look at this one, when the this K is less than J, K is less than J. This how to say, this part will commute with SJX. So therefore, bring that part of the UKT into here, and it just become. You don't need to worry about this. So the important part is the exponential of. Okay, let's go L. L minus 1. Okay, so the first element is part is this one. So this one, you can use this transformation. You can use this transformation. Even this one is even. If it is even, just operate it just 1. 2 pi I times some integer. So therefore, they commute. If it is odd, you can use this one, this computation ratio, to get that effect. Okay? So therefore, it doesn't affect anything. Now, so this part is intact. How to say? Do nothing. So now, next we need to take a look at the point thing. So this is L and L plus 1. So both is okay. Now we need to use this transformation because now it's LC will appear, right? So here you have e to the pi I, SLC, and SL plus 1 up here. Okay? Inside here. And you need to consider computation ratio between this side. But you can apply this one. If SL plus 1x is plus minus 1, or if it is an odd, you get a minus sign here. Minus sign because of this computation ratio. Okay? However, if it is 0, this just operator is 1. Okay, this operator is 1. It's simply just 0, right? 0. So the e to the pi I 0 is 1. So therefore they commute. And they commute and it becomes plus 1. Okay? Therefore, what you get is that this way, and then Lx, and then the same thing, exponential of pi I sum over L as JSP, and then it's L plus 1x. Okay? If you do that, so this one is equal to S plus minus SLI. Plus is when Sx eigenvalue is 0. If it is the eigenvalue is plus minus 1, you get the negative. So therefore this can be replaced by e to the pi I SL plus 1x. E. Yes. Okay. If it is 0, it becomes plus 1. If it is plus minus 1, this will become minus 1. Okay? So therefore, this is it okay? You have a problem? And for the sake of the convenience, I just write down like this. Is it okay? Do you need it one more time explanation? Okay, you need it. So, what's relevant is the e to the type I, SL, Z, SL, X, e to the type I, SL. If SLZ is plus minus 1, sorry, what I'm talking about. No, it's okay, it's okay. And then you have an e to the type I, SL, 1, X. Oh, yeah, sorry. Sorry, L plus 1, X, e to the type I, X, L, SL plus 1, X. Now, SL plus X is equal to plus minus 1. The problem is reduces to this one. Okay? So that's, or you use a minus sign. Okay? If SL plus 1 is X is plus minus 1, this becomes minus 1. Okay? So therefore, this identity is okay. Okay? On the other hand, SL plus 1 X is 0. This operator becomes 1. They commute, and it is plus 1. SL plus 1 is X is 0. This is become plus 1. So therefore identical. Okay? Now, if you increase plus 1, it becomes this L plus 2 and L plus 2. Okay? L plus 2. And this becomes L plus 1. But what's relevant part is this part and then this plus 2. Okay? So the other part is irrelevant. The same game. The same game will give you another term, something like e to the pi I, SL plus 2. Okay? Now let's increase this one by 2. It becomes 3. It becomes 2. And 3. That is included in Kennedy-Kawasaki transformation. Okay? So therefore, what should end up is like this: pi I S X to the L. So therefore, this transformation is something like that: L X e to the pi I sum over S. K and then X K equals to L plus 1 and then capital L. Is it okay? Is it okay? So now let's erase here. And for the sake of this simplicity, let's do first this one. Fine. Okay. So now what you need to worry about is the pole. So what here we need to the first non-trivial part appear like this way. Like this. Okay. Am I correct? Yeah. and correct. Okay, now if this part so if this part, the summation part is odd, we can apply this to the rotational version of this one. So we have like SPE3 minus cos charge is x e to pi I is x equal to minus this. If this summation is odd, we can apply this rule to get a minus sign. Okay? So therefore, this is exactly equal to e to the pi I sum of j equal to 1 to L minus 1 is JC is Lx to the 3. If this is equal to 2 pi I times something, so it's always become 1. So therefore, if you commute them together, you get a plus 1. So therefore, and also this is, if this is the summation part is even this is plus 1. On the other hand, if it's odd, if you apply this rule, you get a minus sign. Therefore, this way. Now, if you increase the number by 1, now computation relation part is SDL, SDL, and SDL. This is always plus 1. Okay? Plus 1. Therefore, you just bring this one into here and you get a 1. So therefore, even if you just increase by one more and 2, and become and it becomes 2, what's relevant part is always e to the pi I SDL, SDL, e to the pi I SDL. Always. But they always commute. Okay? So therefore, this is always SDL. Okay? Okay? So therefore, oh, sorry. So this is B. So therefore, so this is equal to e to the pi I sum over L, or no, L minus 1, j equal to 1, SL. So is that okay? So what's the relevant part is over here. So the other part is irrelevant. And this part is just like, also this is J. Fine. Finally, like this. Now, this one, can you guess what's going to happen? So the first relevant part here is e to the pi I, sum over j equal to 1 to L minus 1 is dj, and then SL x, and then SLY, e to the pi I, the sum of this one, and then SLM. Sum over SDJ, j is equal to 1 to L1. So like this. Now, the computation ratio we have to use, we get u is equal to y and now y. Okay. So SLX e to the pi I SLX and SLY and the e to the pi I SLX. Okay, so if you use this rule, if you sum is odd, you get a minus sign. Sum is even, you get a plus sign. Okay? So therefore, e to the pi I, sum over j equals to 1, L minus 1, bj, SLY should show. So this one is equal to e to the pi I, sum over L minus 1, j equals to 1, sj, z times SL. Okay. So the sum is odd, you get a minus sign. Sum is even, you get a plus sign. It's the same rule as before. Okay. Now, if you increase by 1, now commutation ratio is SDL. Here SDL and SLY. So SLZ, SLY, SLZ. Okay. So what we need to use is at the point thing. Okay. Okay. So relevant part it becomes like this. Relevant part is always become like relevant part is e to the pi I SL C SL plus 1 x e to the pi I like this. And if you apply, if the Sx L plus 1 is odd, we can apply this rule, get the minus 1. Okay? As L plus 1 x is 0, then you get a plus this one times this. So therefore, this is equal to SL pi e to the pi I SL plus 1 x. Like this. Okay? And if you increase the k here, k by 1, this becomes L plus 2. It becomes L plus 3. But this SD part is here, learnable part is L. Because we just take a computation ratio as alpha. So therefore, this becomes 2. And then they keep multiplying. Then what you get is e to the pi I, sum over j is equal to L plus 1, L x j, like this. Okay. So this is the consequence of Kennedy-Takasaki transformation. Any questions at the moment? The transformation is very non-local because the original UKT is very non-local. Okay, so this is the non-local part is really this part. These part. Okay. And it really looks like a Jordan-Bruner transformation with same before. But Hamiltonian we look at is not the single S, okay, but 2S. Okay. So therefore, there's something here also happens. Maybe we can. So Hamiltonian we're looking at is something like this. Okay. For L. Oh, sorry. Hamiltonian, so this is the Eigen-Hamiltonian. And you just apply UKT. UKT. And this is UKT SB L UKT UKT SG L plus 1 UKT. Okay? Apply this rule. Apply this rule. And what you get is that the e to the pi I sum over L minus 1 J equal to 1 is J C S T S L C and then e to the pi I sum over L and J equal to 1 is J C and S L plus 1. Okay. Is that okay? But now here if it is even or odd, okay, even or odd, what's relevant part is this plus SLC in the exponent. Therefore, this part just cancels. And what's left is that the b to the pi I is PL, SLC, SL plus 1 t. Okay. Now, even though this Kennedy-Takasaki transformation for single spin operator, you have a non-local term. Non-local term. Like it's like here. So you have a side like this way, and for Sx you have SL like string is become like this way. Strings moving to right, and this non-local operator is moving to right because just k is now from L plus 1 to capital L. On the other hand, for SC, strings moving to like a left side because j is running from 1 to L plus 1. For SY, you have a both. You have a both. This term and this term. However, if you have this quadratic type term, these string cancel. These string cancel. So if you have so this string cancel, and what's left is e to some power at that side. At that side. So therefore, the Hamiltonian becomes local. Very local. The same thing happens for Sx. Takasaki, and this is equal to e to the and this is always equal to minus SLC SL plus 1. So that's what really happened. Because here if SL is 0, this term is 0, right? Okay. So therefore, what's relevant is like a plus minus 1 bar. So therefore, okay, so this is minus 10. The same thing happened here. This is the E which pi I is X. Okay, L plus 1 L plus 1 is Lx SL plus 1x up here. For the same reason, you have SL x and SL plus 1 x will. Is that okay? And then so you can do SY L SY L H1 you can do it in fact the following thing. And then here one. Okay, that's really hard. Okay. So this one you cannot simplify because whatever value SLY takes, we don't know the value of it. Doesn't affect this. Z and X part is independent. Okay, independent direction. So you cannot simplify like this. Okay, so now for H tilde, lambda D is U Kennedy Takasaki. H lambda D, U Kennedy Takasaki is something like a point. Like this. Okay, you come very long. Oh, lambda. Thank you. Okay. Okay. Okay, so this Hamiltonian has the following has a D2 symmetry. So this D2 is the okay, D2 it sounds like this one. So X direction, Y direction. This is by I rotation. This is 0 rotation. By I rotation. This is actually Z direction. This is Z direction. Yeah. So if you rotate to X, so let's see. So this if this is the X direction, if you rotate X, if it is this X direction, so if you rotate pi I, this black side is going to move to the for you guys left side, the black part is left, but if you rotate the pi I, you get your side, right. You just bring to the right side, right? And next to Y direction is this way. And if you rotate Y direction like this way, in pi I, right? So pi I is, oh gosh, it doesn't do anything. But it does do something, but I cannot distinguish. I shouldn't use this one, but like this way. But that is equivalent to the Z rotation. You understand what I mean? Okay, so what's the best way to explain it? So what is the best way to explain? So x direction pi rotation is this becomes like this way. If y direction like this, and just becomes like this way, right? And that is the same as if you start with like this way and then just do the rotation around z direction, it becomes like this. Okay, do you understand? So therefore, yeah. So if you do the higher rotation in x around the x-axis, yeah, x-axis, you get that z2, non-trivial z2 element. And then if you have a higher actual y direction, you have another z2. But if you compose it, you have a rotation in the z-axis, higher z-axis. And then this action is invariant under this z2 rotation, z2 cross z2 rotation. Because I mean, you can see from here, so if you have sx is transformed by sy direction by pi I, okay? Pi I, in the minus sign, right? But here you have quadratic term, minus times minus is 1. So you always have a minus sign will cancel. The same thing happens everywhere. You have even if you have a higher rotation, you get the non-trivial rotation will be minus sign. But this quadratic term will cancel these signs each other. And this linear term is e to pi I, it doesn't matter. Because if you have a plus sign and a minus sign, it doesn't matter. Because it's e to pi I. So therefore, this has a z2 cross z2 symmetry. So, if you, yes, z2 cross z2 symmetry. This is exactly the manifestation that if you, oh yeah, sorry, I think I should have mentioned. So this Kennedy-Takatsuki transformation. Sorry, I forgot to mention. Okay, let me write down the definition. Okay, you Takatsuki transformation is K equal to 2 to L. The combination of planet sum over. Yes, G is equal to what? Like this way. So here always we look at the there's a 1 to L, and then you always have an n. So it's only well defined open, like open. If it is periodic, you cannot like simply start with 1 and then just take like this way. So it's always considered open chain. So this Kennedy transform. And as I mentioned, open chain. So this AKLT balance bond state, you always have H model will appear at the end. H model will appear. So this will give you C2 freedom, and this is C2 freedom. And that is, if you do that, Kennedy transformation of this, whatever, this lambda D Hamiltonian, so this H lambda D Hamiltonian has a D2 symmetry by explicit rotational, other exceptional rotational symmetry. So that's become manifest. And then furthermore, okay, you right here now? If you apply the system, and do the same transformation as so same transformation And what's left is the following. Okay, suppose you have x and x. Okay. So the schematic figure is something like you have a site. You have a site like this one. You have a site. As I mentioned, the string. So if you have an x here, if you have the side, if you side I here and side j is here, something like this one. And then if you perform the Kennedy transformation, you have a string is moving to the right for the x part. So this string part is moving to right. Then the same thing happens here. This. And they cancel. They cancel. And what's left in the middle. Okay. So therefore you have xi, x e to the pi I, sum over L, I plus 1, j minus 1, x, L, and then sj, x, like this. Okay, the same thing. So let's suppose if you do the z, what's going to happen is the opposite. Strings moving to left. Strings moving to left, towards left. But at the end of the left end, they cancel. So therefore, what's relevant is the middle. So therefore, it becomes D and D and D. So like this. Okay. And now we can do this is also the exercise. If you do the Y, so both okay. So here SE to the SC part. And here you have an E to the pi I, SX part, E to the pi I, SX part. Then you need to so you need to combine the effects in between. So here you need to have E to the pi I, sum over L is equal to I plus 1, J minus 1, something like that, SCL. And then here you have E to the pi I plus SX and L. So like this. And then I think you need to use some commutation relation to get the correct. So, this part. Oh yeah. So this part is. Okay. So this one is just like this one. You got like this. Okay. However, so I mean, if you restrict yourself to x and z, it's really like this. I call it the Nielsen order becomes string order. String order. I think z is that. Okay. So this is the we define the whole string before. So that's all string. Okay. Okay. So now, and vice versa. So SI D SJC is equal to U Kennedy Takasaki order string IJ. So IJ U Kennedy Takasaki. Okay, so that's what's really happening. So and then is the Kennedy Takasaki, and then here you have an order string, and then here I and J. So this is I and J, and then this way. And then you have a SI, T, SJ. Now, we know that the distance, so in H lambda equal to 1 and D equal to 0, we know that this all string Ij limit I minus J equals to infinity is non-zero. 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 So that's the expectation coming from the AKLT. AKLT. So that's we already computed. In AKLT case it becomes 419. Actually, it was 419. So that's we computed. So go to the zero side, lambda is equal to 1 and d equal to 0, and you just put that Kennedy Takasaki transformation. Then here, what's going to happen is that the limit I minus j goes to infinity si d and sj d is non-zero. But the very, very non-trivial thing happens. So this is long-range interaction. Okay. So in the original AKLT, Si as j is the exponential decay. But now, if you go to the zero side, it becomes non-zero. Because the string of, so what's really happening is following. So that mentioned. So that there are 4 degenerates rounded up here. However, once you think about here, one out of 4 ground state E2 plus E3 is spontaneous broken. Spontaneous broken. And this expectation value is exactly the vacuum, one of the vacuum you pick. So if you look at this H here, so that all the interaction is local. So we expect the short range order. However, once you pick one of the ground states, and take one of the ground states, D2 cross D2 symmetry is spontaneous program. Then suddenly, long range interaction emerge. So that's the consistent of this project. Remarkable thing, energy Takasaki transmission was solved. Okay, and then so the reason why so I just so large number so D2 in between x-axis, axis, okay, and large D, or trivial large D equals to infinity, which is trivial phase. Trivial phase. So this is unbroken. Because I mean, all the state, ground state, all the state, if you look at this one, all the state Z is actually 0. Okay? Z is 0. So therefore, even if you rotate the x-axis by pi I or z-axis by pi I, it's just 0. Okay? Down problem. So Haldane phase, so you have both of them. Once you pick the vacuum, D2 cross D2. So this D2 cross D2. I mean, it's okay. Either side, y-axis, z-axis, either side is okay. Haldane phase, arising anti-magnetics. So if you look at that, so lambda goes to infinity. So lambda goes to infinity. So this term is relevant. The Hamiltonian still has the Z rotation is okay. However, this is off to pick the vacuum. So in arising Hamiltonian, so the anti-paramagnetic is something like so plus minus so in the open end you can like this anti-paramagnetic. And then even if you rotate the Z axis, it doesn't do anything. But if you rotate the X axis Z2, it becomes an opposite spot. Okay. So the two ground states. One is plus, the end is plus, and minus plus minus plus. Since we are concerned like open end, there's an end here. So it starts with plus, and then it's an anti-paramagnetic order. So plus, minus, that is the thing. Or you start with minus, and then minus, plus, minus. So there's two degeneracy. That is exactly the one which is not, which acts the D2 in X direction acts non-trivial. Even if you rotate in Z-axis, plus doesn't change. Plus is plus. Spinning up, there's a spin up, right? Even if you rotate in Z-axis, it's spin up. So therefore, it doesn't change. So that is unbroken. But for X, Z2 is, so Z2X will swap between these two. And then if you pick one of our back here, these two symmetries are broken because D2X move to the other back here. So once you pick the back here, D2X will be wrong, spontaneously symmetrical. Okay, so that's what I wanted to explain today, to be honest. And then for time being, okay, let's slightly explain about this speech. Okay. Okay, so this is exactly what's really happening. Is that so if you impose Hamiltonian as a D3 plus D3 symmetry on Hamiltonian. So the ground state, actually, for Haldane phase, the ground state will break spontaneous. Once you pick the ground state, you have a spontaneous symmetry break. Whereas for trivial states, the ground state does not break the D2 symmetry. So therefore, this spontaneous symmetry breaking would tell you that two phases are different, even though they can be connected with this symmetry in the Hamiltonian. Okay. So the symmetry protected so symmetry. So this will lead you to symmetry protected topological phases. Okay. Is a notion of in this is 2009. 2009 as far as Gu and West and the Pullman and Moshikawa. The one thing for Hamiltonian has a D2 plus D2 symmetry. And trying to move one phase to the other phase, you really need to have the phase transition non-trivial. As I mentioned, so it's a gap state. So HS. So S. Okay, so this is the non-trivial energy. The first ground state is non-trivial, but you take. So this is the S. And then SH whatever, and they both are gapped, but so that if you put the energy of the gap first excited state, the gap states on both ends, you have to have the non-trivial energy for first state. But once you change the S, there's some point that hits to it becomes the degenerate in ground state. And there, this phase will from the trigger phase to Haldane phase. And that is only occur when you impose the Hamiltonian as D2 cross D2 symmetry. So the symmetry is protected. Hamiltonian symmetry protected. And topological means that the bark do not have the bark is gapped. Bark is gapped, but only the degrees of freedom will show up at the edge. Bark is gapped. Topological means bark is gapped. And then the phase is phase is one phase is once you pick vacuum, the DC plus DC is broken, but the other is not broken. That's how what the people in 2009 problems. So that's what I wanted to say. And the last lecture, I will talk about little bit about something called slightly mathematical notion, something like projective representation of DC plus DC, or SO3 or whatever, or SO3, and then something called group cohomology. That's my plan. I may change my mind to group cohomology that distinguish these two phases for the trivial phase and hard group that you can use to distinguish by using some mathematical notion for group cohomology. That is plan, but I may change my mind. I don't know. But I haven't prepared a lecture, so sorry about it. Okay. Let's stop here. And one student who emailed me about some research and so on. I forgot the name. So if you, just read the chat after. Good, that's all. F over the A 好的 C 管，我们的 C 管对这里的题是的例子，所以呢 C 管 F 以 D 这个数的话就可以，他们解的可以就是方法。他们的太迟了，这样。类似于要是预期上学成的，他们那个应该是这样。它是 S W 的这个我是反正就后面是一个咱们这个公司的一个系，一个地在这边这里，那做的这个点。得到的让这个这个看它的性质和大部分然后如果你知道了这个，要算这个是无极，但是如果你是一体的话是负，然后我知道这样的这个线啊，对这个线索。那这有几也是，分析哦，I 啥事情？他就会把这个一就变成。And you were interested in the car for two years ago.这个更加是往上4这样，别最多上。这个话题会有两个后讲这个对好，然后非常好的，然后会抓这个一个话都是重要的，因为在 X 过去就是它这盘就是这几节，还有点每个 S 这个这里
所以这个 SL 加1就那个叫真的，所以说还有正负一和负一都是9，证明是一样的，证明它跟正 I 还有反派一样的，那个场都是这样，你看这样正就行，这个是反其实放到这里可以这玩意就可以套这个，你看这个这个就下标一样的操作，所以它就是只有这个几项，哎，对，看到啥全部都是可以互相抵消，就是因为也就是这样。我是从数学上，最后面你把这个展开，那个最后就是这样都是。然后前面东西对，因为这个就肯定是，因为下边不止这个对这个记的时候他也注意，直接给他处理了一下。这是我前面这样来的，后面别跟我这门课这样的相处，他就都是看 IT，这个正的也大家都一对三，对，前面全都是就只有这样做，这样做就把这玩意儿加中间嘛，这样就很容易出来，这就是负的。啊，对，然后推回来就是这样，然后推回来就是这样。
为4元区，它是有2个那个，
你看我这些。正在就
我刚才它的成本有个上面讲的是所谓不定义不变，也是能给
没有人去想。
Yeah, so I have too many students.
我家里确实不一样。
So
这证明它就变这样。
这是什么？
Okay. So I just refrain myself from taking almost.
他说的反正这是招3个整体型，每次都去派的选专，然后你先让 S 转一半群，然后再招半转半群，像我就没招全专，
没招。这套证明
他就是把这样结构的一个。他说那个东西仍然是满足那个 S。他就说，如果他有什么细分标准，他还满足 CR。对吧？因为他这个给了最后完之后，你把它统一成一个设计就是这样，就是原来 CY 的排列，因为它是依照那个证明来设计。然后就把背后的一起看。这个是新证明会导致这个情况。大概就相对不一样。但是它这是 P 一起交往。
So now these top issues.
然后后面其实跟差不多一样，对，后面差不多。
就是这个配音变化成啥来着？
对，我会跟后人讲。
后人就过来了。可惜的是，这段那个书讲一趟也没用。
对，我感觉这样子就人家就是用 UG 定义是前面这一题，是他定义记录，然后还要记录一个这个，他这个性质要记录。对，这个性质要记录，一直循环给你记，所以它就负一和代表做一下。然后它这个它因为我记得OK 真的，对，还有这些东西，这东西我怀疑是从这东西对，给它连出来就是那个你要在连接后边那东西，这样对他讲，对他讲，对他讲，你都怀疑参加那么难。
我觉得其实就是的话，这2个交换一下，然后2个就相对。
不能这么简单的话，
交换
这个不能这么简单。
这个反正结论是对的。
Can you
然后就
try to derive it from Houston? And you can send me a note. I want to check it out.
这个然后这个这儿是加的加东西。
这个正常，这个就。
现在还没翻。因为就是
OK。
因为第几还有一个大点，就是其实某一项，对，就是这某一项，我还没拿出来。然后这个东西其他这个东西，主要是要分头。如果 SO 加1 X 这个意思，啊，但是这里面就是就是1等于它这个这是1康1乘2就是这个。如果这个就 X 对正证明是这样，因为正的话应该是派 I， 然后负的话就是派，这样派正派这样。对，所以它这个东西要就考虑这个。正派这一个负派对。就是先这里，先跟你讲证明是一样，这样就跟反跟紧张。 然后我们就还这地上就相当于一地方它这个并让它展开这收割，对吧？因为只有这一项到这个公式，跟这个项目是一样的，因为这个有部分它是故意的，也相当是故意，所以你可以完全写开来应该是这样的。对，你会这样的，就把它一个 e 的什么，就是派 i 第一，或者派 i 或者啊 e 的 SL 对5千，然后这个是一个 SLS4，好，这边因为这所有东西互一学完，我就把它换了一个倒序，因为这边是 e 的派 SL，e 的派 SL 减然后因为这个东西就是出来这个。
前面写的那个是，前面这上面是错的。
不正是一样。对，非段是 y， 这是 y。然后其他这些反正因为跟它还是不一样，所以可以给你放上去，把它这个对，所以它非段就这个。最主要是因为刚刚跟你讨论，然后你把它写成一个事情。OK， 这个再来随意的派，这笔的时候然后后面清理，其实应该可以证明，但是我就同意，就是加这个对比这个，然后加这个外界就这样。然后说共享对就是他把这个，因为这个 U 当然 D， 对，当然 D 的重点，对，所以我们要考虑加2个，然后不考虑加1个，对，但是加一个解决才对，加2个，这样这个关键步骤就是差一个对，差一个，这段累积对刚刚这段累积，然后就是刚顶带，对就下一步是这样的是一的，就这样送给我，因为这个还没到再到1点，对，这儿可以放过去，放过去之后，把变成不看，然后需要了，这个看法是一样的，因为不来这领领手的话，它另对那个，然后顶正面的时候看就是2.4这些不，本来160毕竟是但是他这个做完手术，
本来就是他都做的一次嘛。
对于我这种偏僻的来说，好的就不止
但是他做这个变化，
那就头，那叫我操，这么感觉去了自然过不了。
然后后面就成一些上被 active， 然后另外然后感觉这样啊，对，这个然后所以他们越做的越这个慢慢就变这样，就这样形式。然后他这玩意儿是一个。类似一个，还有这种两边讲说夜发的研究是自全的夜嘛，但变成那个做电子的时候，就是这个天地线成为做事情做之后有这个做的时候就干脆，上面都地方是不是？然后这个是有这个因为它是有4重减配，我那个啥因为这个然后这个出来关系，他发现这个加2这个手这个然后这个那个发现啥？发现然后呢这个左右两边再整个就可以提示，然后一边然后这边这个啊对，就这样然后就发现啊，上大地我觉得是不是那这
在菌看里面多少就，然后我们之前那个节目，当然一定给说这个这儿，
下一题
这个他们家这个就也可以，我下一题说明还有，就因为你在养无血的之前是相关问题，这个反映这个两个之间的关联，就是不得说明无确定出两个对还有关联，是不是还没有？
过来建议。我的那
我考前，
然后变完了之后这两个人，
但是而且
然后你就是咱们这个不接触8米，因为它有这个，它有这个什么，
这个它是4节的呀，
哦，就是它是最开始是从开店的那个，它就是这边没有关系。自己听这个区别，它是4个字4种姐妹。
这个既可能没实际在做实验，
这个确实。样子里面那个，然后自己品凹到也高也对是一个，然后它就它就突然就变成一个艺术和一个就在选这个部件有没有
？Then you need to calculate more like correlation function by using distance, but not distance.
我上一期是这么，我这一期我估计
你把它 pick 出来，它就。
就没了，然后有可能没比就是转一转这个。
但是地热你本科地热你也不需要，有必须的来绕1个月还能够就是我自己的家的家，对呀，你本科地设要做1个月能够。
我老师意思就是差不多要做出来一个，
他如果真的是技术，有一定的，比如说绕 X 轴，
我确认一下，他说的非常基础。
特别把在科研方面非常基础的，确实，对于他们来说非常难。
知道这个那
哇，他这么说，那我接下来做一下，
这个这个
非常这个
非常的这就我刚刚
这不是已经是上星期
对，
项
目对，业那我觉得他也别太少，别这只要
他一定是10，然后对象这些一个一句话相似于一个对象，这些
这个也是，
那跟他完全不对。